We will move on to the next presentation. It will be by Mohamed Nedal, entitled Predicting the Solar Energetic Proton Integral Flux with Deep Learning Models. All right, I'll give you, in 10 minutes, I'll give you a sign.
Hi everyone, it's nice to see you all. My name is Mohamed Nedal. I am a PhD student at the Institute of Astronomy in Bulgaria. And today I'm going to give a brief overview about our recent work on forecasting solar energetic proton integral flux using the pi-LSTM neural networks. So first, the SEP events are mostly composed of protons, electrons, and some heavy ions. And there are two main categories, gradual SEP events, which are usually associated with CME-driven shock waves. And there are SEP events associated with solar flares. And this is the characteristic curve for each type. And the characteristics of SEP events are strongly influenced by the properties of the associated phenomena and the interplanetary medium. And there is a very strong correlation between the SEP and the solar cycle because it's increasing with the solar maximum and decreasing with solar minimum. However, the exact relationship between the solar cycle and SEP events are not quite understood yet. And the acceleration, transport, and creation mechanisms of SEP are still under research, and they are very complex because they involve the combination of magnetic reconnection, shock acceleration, and wave-particle interactions. Currently, there are several models for forecasting and classification of SEP events, and they are mostly physics-based models, machine learning models, empirical models, and hybrid models that combine different approaches. And there is a very recent nice review that combine all these models. So in this work, we are developing and training bi-LSTM neural networks to predict or forecast the integral flux of SEP, solar energetic protons, at three different energy channels, at three different forecasting windows. And these results for this work could be implemented in these frameworks to model the space radiation profiles. And this work actually it can contribute to the growing literature on this topic because currently there are quite few models that can predict the flux of SEPs. So initially these were our data sets. So these are our features, the time series of logarithm for proton integral flux, sunspot number, F10.7 index, the logarithmics of X-rays at two wavelengths, and the solar wind speed, and the average magnitude of the interplanetary magnetic field. These data were obtained from the Omni dataset, but initially we trained our model using this classical data splitting. The blue is training data, the orange is the validation data, and the green is the testing data. But we found good results, but they were a bit biased because the testing data were almost toward the solar minimum. So we tried different approach. For each year, we took the first 9 months as the training set and the second 2 months as validation set, and the last month, December, is the testing set. So we did this pattern over almost 43 years, comprising our 4 solar cycles of a data set. And the data starts from 25th of December 2076 until July 2019. So this is how it looks like. And to see how the data are correlated in the features, these correlation matrices shows the training set, the validation set, and the testing set. And we can see here the first 3 rows are the logarithmic time series for the proton flux at 10, 30, and 60 MeV, which are our target features. But we trained the 3 different, individual models. To convert this time series to a format convenient for the BiLSTM models, we implemented this windowing method, which is called the multi-input, multiple-output strategy, or MIMO strategy. So let's say this is our first sequence of data. So we define the input horizon of data, and we set the output forecasting window. So, and then we shift by 1 step, and we do the same for the second sequence, and so on. And for the forecasting windows, we pick the first step here, which are in purple color, and we set this as the 1 day ahead forecasting. And the second step in orange are the 2-day forecasting, and the last one in green are the 3-day forecasting ahead. So in our, So in order to do a comparison, we did benchmark of 10 models. And initially we were aiming for the LSTM models. But after we did this, we found that the BiLSTM models performed better. So first here we have the naive model, in which we assume that the next value is the same as the previous value. And we have here the moving average model. So these 2 models are very simplistic, and that's why it's very, they have very high error. And this is the Hubbard loss. We use the Hubbard loss function as our loss function because it is less sensitive to the outliers. So we have here the linear machine learning model, the dense machine learning models, the recurrent neural network, stateful RNN, stateful LSTM, the BiLSTM, and stateful BiLSTM, and 1 layer convolutional neural network with LSTM. So the machine learning models in general are very close to each other, but the best one was the BiLSTM. So we proceeded with this model, and this is the general architecture for a single layer in the BiLSTM model. It's composed of 2 layers. One is the forward layer here, and the second one is the backward layer. And the blue circles are the given time steps. The green boxes are the activation units, and the purple circles are the output time steps. And the orange and yellow circles are the hidden states in both layers. So after we trained the model, we found this is the loose curve, and we set the maximum epochs as 50 because we found that from experimentation, after 50 epochs, the curve, the error doesn't change very much. So here we have the loose curve for the 3 channels for the training and validation set. And we have here the mean absolute error used as a metric in the model. And here we have the learning rate of the Adam optimizer with epochs. So we used the callback function. It's called, it makes the learning rate decrease a little bit by a certain amount when the model trigger plateau. Like if the error if the performance of the model didn't change much, it changed the learning rate in order to converge better. So for this is results for the testing set at 10 MeV. On the left side, we have the observations, the real measurements on the x-axis, And on the y-axis, we have the output from the model. And we can see there is a very high correlation between both in 1 day, 2 day, and 3 day forecasting. And on the right side, we took like a filter all the values above 10 particle flux unit, which is the threshold by NOAA. And also we found a very high correlation above 70%. And the same for the second energy channel and for the third energy channel. And this table summarizes all the results. So the first table here is the validation set, and the second table is the testing set. And we have here the 3 energy channel. Here we have the model laws and model metric. And for the 3 forecasting windows, we have the 4 error metrics that quantify the performance of the model. So in order to see how the time series data, the output from the model is correlated with the observations, we did the time series correlation, in which we took a certain number of time steps, and we calculated the Pearson correlation, and we did the same pattern over the whole time series.
5 minutes.
Okay, thanks. And we got something like this. So on the left side is the validation set, and on the right side is the testing set. And here we have the first 2 plots are for the first energy channel, here for the 30 MAVE, here for the 30 MAVE. So the blue and orange are the observations and the model data. Everything here is for 1 day step ahead, 1 day ahead. And here we can see this brown dots are the correlation factor over time. And this golden dashed line is the mean value. So in general, as we can see, it's very high, like in general. But we found that there are, in the testing set and the validation set, there is a drop in the correlation, especially at the solar minimum. And these are some data segments from the testing set for the 10 MAVE. And here the blue curve is the observations, and the other 3 colors are for the 3 output forecasting windows. And also we can see like the model could identify the onset and the end time of the SCP events quite good. And the general profile of the events also could be modeled with high accuracy. And this is for the second energy channel and for the third energy channel. So in conclusion, we developed and trained bi-LSTM models to predict the daily average integral flux of SCPs at 3 energy channels using data from Omni database, and we benchmarked these results against other model architectures. And the data splitting strategy that we used, it could maintain the temporal logic, the temporal evolution of the data, and we obtained good generalization without doing cross-validation. And the model did reasonably good forecasting for the 10 MAVE and 60 MAVE, and also for the 30 MAVE. But for this channel, we found it has the highest error, and this needs to be investigated more in future works. And this work is demonstrate the potential of using the bi-LSTM model to forecast, to be used in time series forecasting in space research and heliophysics in particular. And currently we are developing other models to do higher resolution forecasting for hourly data, and we would like to include the characteristics of coronal holes as well, because we didn't include the coronal holes in this work. And that's it. Thank you very much.
Thank you. All right, questions from the audience? Pierce.
Mohamed, that was great. Thank you. Can you say a little bit more maybe about, you were saying that you get the overall trend for the different energy channels, but like I guess the absolute, what is it? Probability, is it?
The x-axis is the time, and the
Yeah.
the y-axis is the logarithmic scale of the proton flux.
So like, yeah, it's underestimating that, I guess, but how
Yeah,
important is that for you? Like, if is the main point of this that we have the start and end times, in which case it's really, really, really good, or do you think you need to do more to actually get it the more exact fluxes?
Yes, actually, it's in general for both the validation and testing set. The model it's underestimating the observations, although it could model the actual trend and the actual profiles. But I think the reason may be because we need to include more features that can give more information. Because, for example, the coronal holes, there is a relationship between the coronal holes and the properties of ECPs and the solar wind in the interplanetary medium, but we didn't include this in this work. So hopefully in the future work, if we add these features, we could maybe notice some improvement in this.
Cool, thank you.
Thank you.
And maybe if I can add, I mean, an importance of getting the flux right would be if you wanted to model space radiation, for example, then you'd want to have proper fluxes.
Oh, sorry. By the way, this table summarize the results for the benchmarking models. So I left it to the end because it has a lot of details. Yeah.
All right, thank you. Any more questions in the audience? I don't see anyone. Any questions online?
I don't see any neither, no.
All right. Well, in that case, let's thank the speaker again.
Thank you.